Last time we discussed water resources and sources of water pollution. We also, of course, discussed global access to water, and then what are the uses of that water, both domestically, industrially, and agriculturally. We also discussed some outcomes and consequences of water use, particularly in the way of subsidence, and then treatment of municipal waste in cities and urban areas to create municipal water. Finally, we discussed avenues by which water pollution has been mitigated across the United States, particularly within legislative packages within the Clean Water Act of 1972. Today, we're going to discuss environmental geology, earth resources, and natural disasters. We're going to begin with a case study of mountaintop removal. This is a form of mining, and you probably have seen evidence of this mountaintop removal here in this part of the country. So what it starts off is as this. Here's the original contour of the landscape. So imagine that you have a hillside or a mountainside that's just sliced so you can take a look at what's happening on the inside. Here we have a forest. And underneath that forest, we have these coal seams where there's, soil interbedded with layers of coal that are, of course, desired by these mining companies. And so we have this high wall mining that removes that coal through boring measures here. And then, of course, we have streams and towns that are nested in this contour. But with mountaintop removal, that original contour is stripped away completely such that the forest is gone and we've removed the overburden that overlays that first coal seam. So the forest and the topsoil are stripped away from the mountain, and then the overlying rock is blasted and scraped away. So you'll notice now we have a piling up of materials here. This is called waste rock or overburden, and it's simply just dumped into valleys that buries those streams that were next to neighborhoods, and it buries other things, including forest, farms, and of course results in floods and downstream water pollution in those areas. And then finally here in the last step called reclamation or reclamation, the mine waste is then smoothed out and the slopes are terraced. So even after some efforts are done to increase the productivity of this land, including adding fertilizer, the plants are still growing on really acidic, rocky, nutrient-poor soil. And so reclamation projects are usually pretty futile in these areas that have been devastated by mountaintop removal. There's a YouTube video for you to watch called Plundering Appalachia, which showcases and shines a light on the coal mining aspects that we see here in our region that's just devastating our landscape. Here's a bird's eye view of some mountaintop removal in Kentucky. You could see what used to be, I call them fuzzy terraces, but forested terraces and hillsides here have been completely stripped away. And that is all for the sake of accessing those coal seams and those interbedded layers of coal in the mountain. So this mountaintop removal is a special type of strip mining. It's often described as strip mining on steroids. And strip mining is simply the practice of mining a seam of mineral by first removing a long strip of that overlying soil and rock. And that overlying soil and rock, of course, is called overburden. This activity is also referred to as overburden removal. And most of the time, these companies that are partaking in strip mining or mountaintop removal, they are trying to access coal for energy use. So half of the coal that's used in the United States comes from strip mining practices. And of course, as you can imagine, that forest and vegetation removal is highly controversial. The entire land surface covering a coal bed can be stripped away. And, in all reality, it's actually a cheap and quick process to access that coal. That overburden, that surface material, that rock and that soil is placed back into the mine. But of course, there's very little or none at all topsoil or revegetation that is actively planted, and any revegetation that occurs naturally occurs very slowly. So in 1977, the Federal Surface Mining Control and Reclamation Act required better restoration of strip mined lands, but these restoration practices are pretty expensive. And even though this act was put forward to increase the footprint that we have on the environment with these strip mining practices, it has positives and negatives. It requires the company to compact the soil, and in some cases, the acidic soil that's left behind really has no way to be unacidified. And so in making these lands greener, after the reclamation has been started, replanting of non-native or invasive species has been the practice. And the planting of invasive species has consequences of disrupting, again, the entire ecosystem. And so, of course, we could do better. And there are a lot of things that have yet to be worked out in strip mining reclamation practices. So we know that Earth processes shape our resources that we have available, including coal, but also other products and things such as petroleum. Petroleum and oil are used for countless products, things that you probably don't even think about, including lubricants and plastics. We're probably all familiar with petroleum being a fuel source, but petroleum is a large product in our plastics. We also have at our inside our Earth precious metals like copper, iron, and aluminum. Those mines produced electrical wiring that brings us power. So we're very, very reliant upon these geological resources that help us produce new technology, including these rare earth metals that are key for making our cell phones and computer works. We also have sand and rock that, of course, is used as construction material. And as you can imagine, the amount that we rely on these geological sources is never ending, and the list goes on and on for examples of products that we use on a day-to-day basis. And I love this little meme here. It says, if oil is made from decomposed dinosaurs and plastic is made from oil, are plastic dinosaurs made from real dinosaurs? Little side note, most of the oil and coal that we extract is actually buried plant material and not dinosaurs or other animals, but still food for thought. So we know that the Earth is a dynamic planet. We also know that the Earth has several layers on the interior of the Earth. Basically, Earth is a layered sphere. There are several different layers, but by and large, we can break it up into three main layers here. The core, or the interior of the Earth, is composed of dense, intensely hot metals, mostly iron, and this is ranging thousands of kilometers in diameter. Solids in the center are concentrated in the center there, but we also have this fluid outer core here. And this combined, this outer and inner core, generates the magnetic field that we experience on Earth. Outside of the inner and outer core, we have another section that is called the mantle. And this is hot, pliable rock. Believe it or not, rock is also a liquid. When it's hot enough, you can melt a rock, and that is what is composing up the mantle of the Earth. It is much less dense than the core because instead of containing a lot of iron, it contains lighter elements like oxygen, silicon, and magnesium. And then finally, the outer layer here, we call the crust. It is the coolest layer. It is also the most lightweight layer, and it is the most brittle layer. And we have the crust forming on this outside layer here, largely composed of igneous rock. And we'll talk about different rock types in a little bit. but the crust below the oceans is relatively thin, but it's very, very dense, while the crust that is on land is much thicker, but it is less dense. So all of these layers combine to, of course, form the Earth, and the different properties, both chemical and physical properties, give rise to those Earth resources that we rely on all of the time. Here we have a table that recounts the 8 most common chemical elements in their percentage in whole Earth here on the left, and concentrated in the crust, the topmost part of the Earth that you and I are floating on here. So in the whole Earth, taking into account the crust, mantle, and core, there's a whole lot of iron that we have, but there's also a whole lot of oxygen and silicon and magnesium. When we concentrate on what is found in the crust, it tells a different story. So we're looking at the crust here, which means we're not concentrated on what is in the interior of the Earth. So iron falls way down in percent. Instead, the crust is dominated by oxygen and silicone. And that is comprised mostly in those silicate minerals that we have on the Earth's surface. We also have a few other things that are found in lower percentages that are considered trace metals in our environment. So what are some primary uses of those metals and materials? Aluminum is extremely important for food packaging and transportation and electronics. Chromium is found in high-strength steel alloys. Copper is important in construction materials and the electronics that we rely on every day. Iron is important for heavy machinery. Lead is in leaded gasoline, as well as batteries, paints, and ammunition. And the list goes on and on here. So there are a lot of different materials that we use in many, many different ways. Tectonic processes reshape our continents and have been for billions of years. And also during that reshaping can cause earthquakes and other natural disasters. So the Earth's crust, that topmost lightweight layer that we're floating around on, is divided into a mosaic of huge blocks that we call tectonic plates. And these plates slide slowly across the Earth's surface like wind-driven ice flows on water. In some places of the globe, this tectonic plate movement is happening at about the pace that fingernails grow, just to give you a sense of how long it takes to shift these plates around. Beneath that, we have magma or molten rock that's forced up through cracks and fissures, particularly in the ocean, that forms new oceanic crust that piles up underwater in mid-ocean mid-ocean ridges. So that molten rock is forced up through cracks, and once that molten rock hits the really, really cold seawater, it begins to condense and form rock. Of course, as these plates move around, they begin to interact with one another. And so where one plate gets crushed underneath another plate, this is called a subduction zone, because one plate is being subducted under another plate. There's a video here that will do a really good job of illustrating how plate tectonics works.
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
I love that analogy. So in the video, it mentioned that it wasn't until the 1960s that people started to accept the theory of plate tectonics. Speaking about theories in science, it's actually relatively new. And so one of the scientists that really pushed forward the idea of plate tectonics is Marie Tharp. And Marie Tharp took raw bathymetric data, which is just data that's collected off the side of ships about the topography or the peaks and valleys on the seafloor. She sat for hours and hours and hours tracing out this raw bathymetric data and actually placed it on maps and understood that where you had these peaks is where we have rift valleys. And those rift valleys are key to understanding plate tectonics. Those rift valleys is where new oceanic crust is created. And so when she brought these findings to her boss initially thought she was not onto something at all, and he refused to accept this find. Instead, at this time, it was thought that the Earth was expanding uniformly from the inside out. No one had any idea about the mechanisms for plate tectonics, and therefore it was not widely accepted. But Tharp was persistent and pointed out that the correlation between the seismological records or those earthquake records and locations on seafloor ridges, eventually she was able to convince him of this idea of these mid-ocean ridges and eventually plate tectonics. So her discovery of the mid-Atlantic ridge, along with the linkage of the major crustal plates for over 64,000 kilometers around the Earth, not only showed, but confirmed the concept of plate tectonics. And she was really one of the scientists to make the theory fall into favor amongst the geological community internationally. And so here we have outlines of all of the major tectonic plates that we have on our planet. These plate boundaries are really dynamic zones, and that's because there is constant movement and pulling downward and overriding. And that's where we have a lot of our earthquakes, specifically in the Pacific Ring of Fire located here along the Aleutian Trench, and then up here off of the coast of Japan. But we also have a lot of volcanism or volcanoes in these active subduction zones. For example, that's why we have here the Andes Mountains, because the Nazca Plate is slowly going beneath the South American plate here. Of course, as you'll notice, anywhere you have collisions, this is where we have mountain ranges. So here was the Andes Mountains, but we also have the Himalayas here with a continent-continent collision instead of a ocean-continent collision here. So the arrows along these lines represent the direction of subduction. So for example, we're having here the Indian continent push into the Eurasian continent here. And then where we have the arrows on the lines, not the black arrows, but the red arrows, that shows which plate is falling beneath the other plate. So these zones where we have these collisions are in the ocean in particular are sites of deep trenches in the ocean floor, as well as high levels of volcanic activity. And the deepest of the world is located at Mariana's Trench, which is out here. So this is what it looks like in cross-sectional view. And so when one oceanic plate collides with a continental plate, because of density differences, the oceanic crust is going to subduct underneath the continental crust here. So while the oceanic plate is subducted or pushed down into the mantle, it then melts because it's extremely hot down here. It melts and causes magma to rise back to the surface, creating the continental volcanoes that we have that are normally found in a line. As well as that subduction zone here, we also have an oceanic trench that's being illustrated over here. And all of this is happening because we have new crust that is being created at oceanic ridges where we have a pushing out to the left and to the right. And of course, that crust has to go somewhere. And so therefore it collides with the continent here. So we have on Earth trenches and volcanic mountain rings along the Pacific Ocean rim from Indonesia to Japan to Alaska, as well as down the west coast of the Americas. And that causes what we call the ring of fire, where those oceanic plates are being subducted under the continental plates. There's a different type of volcanism that we'll talk about in a little while, but still to focus on the subduction zones. These are highly interesting sites for research. In particular, I've been fortunate enough to go to the high Andes Mountains and study the microbial communities that inhabit hot springs as a result, that are formed as a result of this subduction. And so here we have field photos from the Catamarca province, which is located in Argentina, where we again have that subduction zone between the Nazca plate and the South American plate. And this is us taking field measurements at such hot springs that are often called fumaroles because they outgas all of these volcanic gases like CO2 and methane. Plate tectonics, one of the pieces for continental drift, which was a precursor to plate tectonics, is the fit of the continents. And so now we have a different continental configuration than what we are estimating to have occurred about 200 million years ago, which is the existence of this supercontinent called Pangaea. And actually, this is not the only supercontinent that we have experienced on the surface of our Earth. It is simply the most recent in our geological past. So geologists actually suggest that several times in Earth's history, most or all of the continents gathered to form these supercontinent assemblages. And because of plate tectonics, these continents have ruptured and reformed over hundreds of millions of years throughout Earth's geological history. And so I put a link here for you to visualize the breakup of Pangaea. We can go ahead and do that now. And so because of plate tectonics, we know that these movements are still occurring, and therefore the situational positioning of these different continents is not set in stone. And so it is really curious to think about and predict what different landscapes and continental positions we might have on Earth in just a few 100 million years. Okay, so this brings up the idea of geological time, and we've touched on this in the past as well. The different eras and eons and periods on our planet are mostly divvied up by mass extinctions or different fossil assemblages. And so the periods and eras in geological time are mainly telling us about specific major geological events. Those events that changed the face of life on our planet. So for example, the mark about 65 million years ago, that's where we see the extinction of dinosaurs. And so therefore that was a good place for geologists to define the Mesozoic from the Cenozoic. But we also, after a extinction event on our planet, we see an explosion of diversity. And so after the dinosaurs went extinct at the end of the Mesozoic era, we had an explosion of mammal diversity on Earth. So removing those dinosaurs made way for a whole bunch of ecological space to be taken advantage of by our mammal ancestors. So the extinction events, they allow the opening up of adequate space and resources for biological diversity to take hold. We get new species through this process through what we call allopatric speciation. And this is speciation as a result of physical barriers. We do now have some geologists who consider us to be now in a new period called the Anthropocene, one that is dominated by humans and human activities that disrupt our natural environment and ecosystem. However, the Anthropocene, although you've probably heard this term before, it is included in many pop sci books, for example. It is not officially recognized by stratigraphers, who are the scientists who are responsible for making up these different divisions in geological time. And they tend to be more conservative in their approach to defining the Anthropocene because you have to have a sedimented layer in the rock record in order for them to consider it a new period. However, if you have heard this term before, know that it is referring to the period of Earth's history that we currently reside in.